everyone, and welcome to this video. In chapter 19, we're going to talk about IV characteristics, which is a different way of saying resistance-related characteristics. And we're going to talk about different materials here to see how resistance behaves for them. We're going to talk about it at a constant temperature. That's an important piece because resistance changes due to the effect of temperature. So the discussion we're going to have in this video, please take it as a given that resistance is, the temperature, I beg your pardon, is constant. So let's take an example, a metal wire, right? Most basic example, think of it as a copper wire. Well, a copper wire, if you were to plot current versus voltage, you're going to see that the current is proportional to the potential difference across it. So you're going to see basically behavior that looks something like this in a straight line. So the current is essentially proportional to the potential difference. And the resistance is going to be the same for all the currents. And the resistance is basically, the inverse of the gradient of this line is going to be the resistance. Why does this happen? Well, quite simply, metals contain many free electrons. These carry the current. And the greater the potential difference, the greater the drift velocity of these electrons. Let's look at another example. So a filament lamp, right? Let's which we have. Let's say it's a tungsten filament lamp. At low currents, what we'll find is that the current is proportional to the potential difference. But as the current gets higher, the current doesn't increase quite as much as the same voltage increase. In fact, the resistance increases at higher currents. So you're going to find the relationship starts off like this, but then kind of, turns a little bit. And then the mirror image is happening on the other side as well. It's a little bit more of an S kind of shape to it. So, and I'll say this is made out of tungsten. W here refers to tungsten. That's the symbol for periodic table symbol for tungsten, W. So the filament is made out of tungsten. At low currents, the filament is going to behave in the same way as the metal wire. But at higher currents, the temperature increases around 1500 degrees Celsius. And the vibrations of the ions in the crystal lattice increase. And they present a larger collision cross-section and reduce the drift velocity of the electrons. So that is what essentially increases the resistance of this filament lamp at higher currents. We can also have a device called a thermistor, which is a combination of the words thermal and resistor. So what we find is just like for metal wire, at low currents, the current is proportional to the potential difference. So your line will start off kind of like, looking like a straight line. But at higher currents, the current is going to increase more for the same voltage increase. So essentially the resistance is decreasing the higher the current gets. So it's kind of an inverted S kind of picture, right? So kind of a straight line in the middle, but then curves towards the ends. So what is happening here? Low currents, same idea as metal wire, right? Potential difference is roughly proportional to the current. But thermistors are semiconductors, and the conductions in semiconductors is different from in metals. And there are far fewer free electrons. When you increase the temperature, that frees up more electrons to carry the currents. And that is what is going to end up reducing the resistance at higher temperatures. There's one further component that I think is worth looking at, and that's called a diode. Let's have a look at that one. So diode is really interesting, actually. What we find is the profile actually kind of goes like this. So initially, for a certain voltage, there's nothing here, nothing's happening, and then kind of like almost goes straight up. So what is happening here? Basically, no current is going to pass in one direction. Once a certain potential difference is reached in the opposite direction, so in this case, it could be for a silicon diode, it could be 0.6 volts. It conducts with very little resistance. Now, diodes are also semiconductors. And and they are designed to allow currents to pass in one direction only. So what I want you to note is there's nothing happening here. There's nothing here, right? There's no line on this side. So current will not pass no matter what the potential difference is. So you may as well assume that, like, it's kind of flat all the way across here. That's how I would think about this one. Diodes are really interesting. The diode is going to conduct only in the direction, in one direction, and that's called a forward bias. And the potential on one, when you reverse the voltage, there's going to be negative bias or reverse bias, and the diode is not going to conduct in that reverse bias condition. So as a result, diodes are actually used to change alternating circuits into direct current. Alternating current into direct current in devices that are called rectifiers. So we're going to look at that in a future chapter, but I thought it would just point that out to you. Important note for you: the inverse of the gradient of this line is the resistance only for a metal wire. For a filament lamp, for a thermistor, for a diode, that's not the case. Resistance is going to be equal to the potential difference divided by the current when that potential difference is felt across the component. So the special case that you have of metal conduction, we call that Ohm's law. And Ohm's law basically says that the current that's passing through the metallic conductor, and I'll say this explicitly, that Ohm's law is for metallic conductors. So current that's passing through a metallic conductor is proportional to the voltage difference, potential difference across the conductor, if temperature is constant. Diodes, as you can see, do not obey Ohm's law. So that brings us to the end of the discussion on resistance. In our last video on this topic, I'm going to talk about a few sensing devices. This is a new addition to the syllabus. So we're going to talk about different kind of sensing devices because we will talk about them more in future chapters. But essentially, some electrical components can be used to sense environmental changes. What are they? Let's have a look at those. So I'll see you in the next video.